So we'll start this lecture by reviewing the KSP equilibrium expression that we talked about in the previous lecture. Alright, so as you may recall, I showed you and provided you with a list of some common ions, some common ionic species that you may be dealing with, which by all accounts are considered to be insoluble in water. But with the KSP expression, we can actually tweak the system so that we get solubilized species, at least to some degree. And you may remember, like in the case of silver chloride, we determine the solubility simply by starting with a solid insoluble compound and deriving the corresponding cation and anions that may form upon dissolution. And at that point, we use the ice table to start the process of determining the initial concentrations, which in this case we know nothing about them, so we assume them to be zero, and the change in concentration, which is based on the either subscripts in the formula or the balancing coefficients of the products. So with equilibrium concentrations, we can find out a corresponding equilibrium expression in terms of x, which then we utilize to solve for the value of x. And when we have the value of x, then we can basically equate this to the solubility of the compound, right? And the solubility, just to remind you, from the point of view of KSP, represents the saturation level, the max concentration of ions that you could have present before they start precipitating out. Alright, we talked about the equilibrium aspect of solubilizing salts, but one aspect that I want to bring back that you may have seen in previous chemistry courses is the idea of thermodynamics in connection with the solubility of a salt. Specifically, I want to talk about the lattice enthalpy and the process of dissolution. Okay, so when it comes down to the solubility of a salt, we are in essence taking a solid neutral compound and we're splitting it up into the corresponding ions, which are solubilized in water. A way to approximate the thermodynamics of this particular event is to acknowledge the fact that yes, the solubilized species are coordination compounds that are being coordinated by water, and the coordination of water is also referred to as hydration. So we could see and determine how much energy it takes to hydrate these cation and anion components, and we can compare it to the energy that it takes to break up the solid salt in the first place. So what I'm going to show you ultimately is how you can approximate the cationic hydration enthalpy, the anionic hydration enthalpy, and we're going to compare them to the lattice enthalpy, which is the energy that's holding the solid salt together, right? If the salt is to be solubilized, and if it does dissolve easily in water, then the sum of the cationic and anionic hydration enthalpy should be a lot more negative than the lattice enthalpy value is in positive terms. So we're going to do an investigation that allows us to derive the lattice enthalpy, and then we'll use that to ultimately come up with a thermodynamic cycle to determine how likely it is for the salt to dissolve in water or not. Alright, so I'm going to start with sodium chloride. Using a Born-Haber cycle, simply stated, what you need to do is set up the lattice enthalpy equation, which is cationic gaseous cation plus gaseous anion forming the salt. That is the definition of the lattice enthalpy. You start with the gaseous ions and you make the salt. Also, we have the enthalpy of formation, which is the formation of the salt, but this time from the neutral elements in their elemental form. And the idea is that both the products have to be present in 1 mole quantity. So you do whatever you need to do to the reactants to make it work out so you end up with only 1 mole of product. Okay, then we use the definitions of ionization energy. The first ionization energy being formation of the +1 cation and removal of 1 electron. Definition of the second ionization energy being removal of 1 electron from the +1 cation, yielding the 2+ cation. Alright, so in the case of sodium, we are basically ultimately trying to go from solid sodium 0 to gaseous sodium plus. So one of the things that needs to happen is that to get sodium plus, we need to remove an electron from neutral sodium gas, and this is regarded as the first ionization energy of the sodium element. And then for chloride, you have to look at the electron affinity. And the electron affinity, the definition I like to use, is the one that involves removal of an electron from the anion. Alright, so this is the energy required to remove an electron from the anion. The same way that the ionization energy is the energy required to remove an electron from either a neutral element or cation. Alright, now the definition that I'm giving you is exactly the opposite of the equation that we need in the Born-Haber cycle. In the Born-Haber cycle, we need to add an electron to produce the anion as opposed to getting rid of it. So the value of the electron affinity that I provide you with needs to be multiplied by -1. Alright, and then finally, all the species need to be in the gas phase. So sodium, which starts as a solid based on the reactants of the enthalpy of formation, need to be turned into gases. And we do that by using the enthalpy of sublimation. And lastly, Cl2 gas, which is the original species we start with for the enthalpy of formation equation, needs to be split up into a single chlorine atom. And for that, we basically use the enthalpy of bond dissociation, but we are only needing to use one chlorine, so we're going to have the entire equation, including the enthalpy of bond dissociation value. So altogether, everything that you see here above the line, if you add it together, it's going to yield the enthalpy of formation. And you can kind of see that everything else cancels out except for the components of the enthalpy of formation. So to yield the lattice enthalpy, what you actually need to do is add all the terms in black, the half enthalpy of bond dissociation, the enthalpy of sublimation, the negative of the electron affinity, the first ionization energy of sodium, add them all together and subtract them from the enthalpy of formation. That's how you find those values. And here's where you look up the values. Usually they'll be presented to you in the problem. The bond dissociation enthalpy of chlorine is 244 kilojoules per mole, so we input that in here. The sublimation enthalpy of sodium is 107 kilojoules per mole. The first ionization energy of sodium is 496 kilojoules per mole. And the electron affinity of chlorine is 349. So we're going to multiply that by -1, so now we have -349. So added together, everything in the brackets equates to -376. And the delta H of formation will have to be another value that I provide you with, which for sodium chloride is known to be -411. So altogether, the lattice enthalpy is -787 kilojoules per mole. Alright. I'm going to show you one more example to kind of convey the whole idea. If you are looking at calcium fluoride, the lattice enthalpy by definition is going to be the sum of the gaseous cation and anions yielding the salt. The enthalpy of formation will still yield the salt, but this will have to be made from the neutral elemental portions and versions of calcium and fluorine. So we have calcium solid and fluorine 2 gas. After that, we have to use the first and second ionization energies for calcium to go from the 0 oxidation state to the 2+ state. We also need to have calcium solid be turned into calcium gas, so we're looking at the sublimation enthalpy for calcium. And then for fluorine, if we start with neutral fluorine, we need to turn that into fluoride, and that is known as the negative of the electron affinity. But we are in need of 2 fluorides, so we're going to multiply that by 2 as well. And then finally, we need to break up the fluorine, the diatomic fluorine, into 2 individual atoms of fluorine. So that's the bond dissociation enthalpy. And like before, if you add all of this together, you will end up yielding the enthalpy of formation. So if you add up all the values in black and subtract them from the enthalpy of formation, that will also yield the lattice enthalpy. So you look up the values. The bond dissociation enthalpy of fluorine is 158. The enthalpy of sublimation of calcium is 178 kilojoules per mole. The first ionization energy of calcium is 590 kilojoules per mole. The second ionization energy is 1145 kilojoules per mole. And the electron affinity of fluorine is 328. So we multiply that by -2 in this case, right? So -2 times 328. If you carry out the entire summation in the black brackets, you'll end up with -1415. And if you carry out the subtraction from the enthalpy of formation, which is -1220 for calcium fluoride, you find out the enthalpy, the lattice enthalpy for calcium fluoride to be -2635 kilojoules per mole. Alright, so there's another way to also look at the lattice enthalpy, and it's via an approximation. The approximation follows the following equation. You have a few parameters that need to be stated. Q plus is the charge of the cation. Q minus is the charge of the anion. R bond is the summation of the cationic and anionic radii. And M is known as something called the Madelung constant, which is associated with the shape of the unit cell of the salt. And the Madelung constant has specific values associated with a specific type of structure that you're dealing with. And here's a little table that gives you a handful of those values. The lattice enthalpy is going to end up being in kilojoules per mole, as long as you input the radii in angstroms. And so if you multiply this by 2 divided by n, and n represents the number of ions, this will actually kind of like equilibrate everything so that it becomes based on the same number of cations and anions for any salt that you may be dealing with. So just to give you an idea, if your salt is magnesium oxide, you have 1 magnesium and 1 oxygen, so that's 2 ions. If you have magnesium nitride, you have 3 magnesiums and 2 nitrides, so that's 5 ions. And if you have magnesium chloride, you have 1 magnesium and 2 chlorides, which is 3 ions. Alright, so let's see how this plays out. The ionic radii is something that I'm going to have to give you in terms of values, because I don't expect you to memorize this entire table. Even I don't know the values. But there's something that you could use to figure out the value of the Madelung constant for pretty much any type of salt. If the value of the cationic radius divided by the anionic radius falls between 0.225 and 0.414, you have a given value for the Madelung constant. If the value falls between 0.414 and 0.732, you have a different value. If the ratio falls between 0.732 and 1, you have yet a new value. But the thing is that this is only true if you only have 1 cation and 1 anion. If you actually have 1 cation and 2 anions, then you have a different set of numbers for the Madelung constant. And if you have 2 cations and 3 anions, you have yet the following value for the Madelung constant. So what happens is that we can look at something like the sodium chloride case, right? And simply stated, what we do is we look at the radii of sodium and chloride. Right? And sodium is 1.16, chloride is 1.67. And if we add them together, we're going to get the value of our bond, which is 2.83 angstroms. Alright, now, the charge of sodium plus is +1, the charge of chloride is 1 minus, and we're dealing with 2 ions altogether, right? So the value of N is going to be 2. To get the Madelung constant, since this is sodium chloride, the Madelung constant is literally 1.74756. Alright, so now we input the value of N, which is 2, into the equation. And quite simply, all you do is carry out the calculation. Divide 0.3 by 2.83, subtract that from 1, and then multiply by all the numbers that you have in here. You're going to end up finding out that ultimately the lattice enthalpy is -767 kilojoules per mole. Actually, excuse me, -67 kilojoules per mole. If you compare that to the lattice enthalpy from the Born-Haber cycle, you actually have a very accurate value. It's not that different from each other, so this approximation does a pretty good job of approximating these values. Alright, so let's do one more example and then we'll move on to the next video. So now let's take a look at magnesium fluoride. Okay, so the charge of magnesium is 2 plus, the charge of fluoride is 1 minus. Magnesium has an ionic radius of 0.86 angstroms, fluoride has an ionic radius of 1.19. So if you add them together, you get the value of our bond, which is 2.05 angstroms. So we input that into the equation. Now, the number of ions, we have 1 magnesium and 2 fluorides. The number of ions is 3. So we're going to input 3 for the value of n. And now for the Madelung constant, what we need to do is recognize that we're dealing with 1 cation and 2 anions. And what we're going to do is divide the cationic ionic radius with the anionic ionic radius. And in this case, we're yielding a value of 0.723. So looking at the table of Madelung constants and sticking to the 1 to 2 stoichiometry of magnesium fluoride, the value of 0.723 falls in between 0.414 and 0.732. So we're going to stick to the Madelung constant of 2.408. And that's what we input into the equation right here. So upon carrying the calculations, you're going to find out ultimately that the lattice enthalpy is equal to negative 1857 kilojoules per mole. And so as you can see, the procedure is not too bad. It takes a little bit of steps, especially to find the Madelung constant itself. But it's actually not too bad once you do it 1 or 2 times. So we'll stop at this point, and in the next video we'll talk about the structure of water and how we use a thermodynamic cycle that involves the lattice enthalpy to determine whether a salt may be soluble or not.